Hello, everyone. Welcome to this week's Crunch seminar. Today, we have one speaker, Professor Chen Yong, whose academic journey includes several roles across various prestigious institutions, starting as an associate professor at the Dalian University of Technology, moving to Ningbo University as a director and first-class professor, and then serving at the East China Normal University as a professor and director, and currently holding a professorship, and it's in the School of Mathematical Sciences. His research is diverse, covering integrable systems, computer algebra, program development, deep learning algorithms, chaos theory, and atmospheric and oceanic dynamics. He has innovated in solving non-linear equations mechanically and in developing the Lie group theory, introducing direct algorithms for Lie group optimization and non-local symmetry solution. Professor Chen, with this short introduction, please welcome to this seminar, and please, you can start.
Okay. First of all, I would like to thank Professor Kanadix for inviting me to have this opportunity to communicate with you. Thanks Toscano, thanks the Nazini. So let's begin now. So my report, the title is Last Pair Informative Neural Network Solving the Integrable System, because the title is Integrable Deep Learning. So joint work with my student Pu Juncai. So outline. Part 1, computer experiments, Soliton series, physical informative neural network. Part 2, integrable deep learning. Part 3, last pair informative neural network. Part 4, summary. Part 1, computer experiments, Soliton series, physical informative neural network. 1. The FPU recurrence, nonlinear science. 2. Nonlinear science include Soliton, chaos, theoretical. The boss of Soliton series. Numerical solution of the KDV equation in Soliton. 5 is physical informative neural network. Everybody is now in nonlinear science, FPU recurrence in the major milestone in nonlinear science is what the king of the whole things with computer physics and math experiments, marking the beginning of the nonlinear science. FPU recurrence in early 1950s, Fermi, Pasteur, Ulam, and Tinsingo conducted the numerical experiments on the first electrical computer in history mathematics and discovered the FPU recurrence phenomena. The FPU problem was the forerunner of the computational physics and experiments mathematics, and also marking the birth of the nonlinear science. In 1965, Kluska and Zapsky obtained the shallow water wheel model KDV equation by taking the continuous limit of the described equation and did numerical solution to it, introduce the concept of the soliton. So, nonlinear science, there are three parts: yes, soliton, chaos, and theoretical. So this is correct. Just 1834, the Russell first discovered the soliton. The soliton in the river, and the soliton generated by the computer simulation. So this butterfly, Lawrence butterfly, a fractal. So the boss of the soliton series in 1965, American mathematician Kruska and Zapsky first coined the term of soliton. So the numerical solution of the KdV equation is soliton. 1965, Zapsky, Kruskaya found this solution, maintain their shape and speed after interaction with each other. This discovery marked the official birth of the soliton series, integrable series, and sparked widespread interest and research among the scientists on the phenomena of the soliton. So this is Zapsky, this is Kruskaya. So physics information neural network 2019, Ricci, Predicaris, and Kania-Dix proposed the former PINN's framework. PINN offer up the new approach of the numerical, solving nonlinear partial different equation. This is article. This article is high side people. By now is 4,293 citations. Inspired by this work, we beginning to incorporate feature of the integrable system into the neural network. So Kania-Dix team, research team published a series of important works in the top international journal. Journal Computer Physics, and Science, and Natural Rivers Physics, and same Journal of the Scientific Computer. Part 2, Integrable Deep Learning. 1. Integrable Deep Learning. 2. PINN plus conservation law. And 3. PINN plus Euler transformation. Integrable Deep Learning. Integrable system. Rich simple space, a beautiful structure, and excellent algorithm. The core is the algorithm. Integrable deep learning, the core of this integrable algorithm. The target is discover new mathematical physics. Integrable deep learning. In 2019, we studied the work of the Kania-Dix research team. As we were engaged in the research of the integrable system, I proposed the concept of the framework of the integrable deep learning. There are 3 reasons for this. First, integrable systems have a rich sample space, class called exact solution, especially local well solution. such as Soliton, Breza solution, and Roggeville solution. Second, they exhibit elegant structure with an infinite number of the symmetry, infinite conservation law, last pair, Pahlavi, truncation, and nonlinear superposition formula of the solution. Thirdly, they possess classical solution method, including inverse scaling method, ISM, double transformation, bilinear method, symmetry method. Since then, we have impact on the series study on the integrable deep learning. Interoperability, Soliton series, and its characteristics. Integrability. For nonlinear PDE, integrability has different meanings. Lux integrable ability, bilinear integrability, Pahlavi integrability, Rivera integrability. Important characteristics. In general, integrable system refer to last integrable ability, which have the perfect properties by Hamilton structure, infinite symmetry, infinite conservation law, and Soliton solution. Progress of the integrable deep learning. The fourth stage, we have studied localized views forwards and inwards problem, including some 3 type solution. Yeah, Soliton, Breza, and Roggeville. Second stage, I think is okay. Second stage, integrable deep learning algorithm in progress. So third stage, completed architecture for the integrable system is our target. So data-driven localized views. This is published by our article, the time. Multi-solution, Breza, high-order Roggeville views, and higher-order rational solution. Periodic views, periodic Roggeville views. 2+1 localized Roggeville. Soliton calculus, vector localized view, and inverse problem. Bright dark solution in Numerical system. Yeah, localized view of the variable coefficient equation. The nearly discover new the solution, new the localized view solution. So same space, localized view solution in the integrable system. Integrable deep learning data-driven solution is the first stage. I think I will study a lot of this. So a second stage, integrable deep learning PINN plus conservation law and PINN plus Mura transformation, the PINN plus double transformation, the PINN plus last pairs, and PINN plus symmetry, close the point symmetry and non-local symmetry. The PINN human Hilbert problem, and the PINN plus integrable discretational. So I give to the our works. First, the PINN plus convolution alone. So the two-stage physics information neural network method based on the conserved quantities and application to the in localized wheel solution. This work is joined work with my student Lin Shuning. So this PINN, just the two-stage PINN based on the conservation. The fixed low plus conservation alone, local constraints and non-local constraints. You can see schematic diagram of the two-stage PINN based on the conserved quantities. So stage 1 is just the PINN give the driving give the data driving solution. The stage 2 plus the conserved quantities M. So there's a two-stage. The first is local constraint. The second is non-local constraint. So a two-stage PINN based on conserved quantities. The governing function, the stage 1, but you can see the stage 2, the plus MSES plus to MSE M. This is conservation quantity. This is you can see is the fourth stage some data driving solution. So comparison between the method of the numerical results. 1, the Soliton multi-Q. The 2, M-shaped double peak solution. 3, Plateau solution, Soliton. There's 4, single peak Soliton. So you can see there's error reduce rate. The two-stage PINN method can be remarkable improve the prediction accuracy and enhance ability of the generation compared to the original PINN method. PINN plus Mura transformation. The physical information neural network method based Mura transformation discovered new localized wheel solution. This for example, this data preparation is an infinite bounding data set of U. For example, is KDV. From this information of the KDV infinite to bounding equation and obtained the modified KDV equation is V. So you can see illustrative problem solving progress. Scheme diagram of the PINN plus Mura transformation. We give to the scheme 1 and scheme 2. Scheme 1 is to directly plus the Mura transformation. The first is KDV. This F1, F3 is you can just modify the KDV. I give the two scheme. So step one, yes, this is KdV equation, initial bounding set. And second, you can see the plus the Muller transformation and modify KdV equation. So the most noteworthy advantage of the method is that we can simply exploit to initial bounding data of the solution of the certain nonlinear equation to obtain the data-driven solution of the another evolution equation with added to the PINN and the most important transformation integrable system, Muller transformation. So it is tailored to the inverse process of the Muller transformation, and the outcomes are different in solving solution based on the implicity express. Two schemes are applied to the perform to bounding to computation experiments to effectively reduce dynamic behavior of the solution for the well-known KdV equation and modified KdV equation. PINN plus Muller transformation. It is implement method of the unsupervised learning. The new data-driven solution as successful simulated to one of the most important results is to discover a new localized well solution, Kinkel-Bell-Tile solution of the default modified KdV equation. So it provides the proposal for a new type of the numerical solution by the few level of the many to one relationship between solution before and after Muller transformation. On the basis of the performance of the two scheme and non-free launch them, they both have their own merits and thus more properties on should be choice according to the special case. Part 3. Last pair information neural network. Last pair and last integrable. Last pairs information neural network. 3. Numerical experiments. Last pairs and last pair integrable. In 1967, Gardner, Green, Kluska, and Muller proposed the inverse scaling method to study initial value problem of repeat DC of the KdV equation. This is one of the most important methods in the modern mathematical physics. This is a very important article. So in 1968, inspired by the GGKM work, last pair proposed the concept of the last pair and creative proposes a general frameworks for use last pair to represent the integrable system. This Lux gave the integral of nonlinear equation of the evolution and the solitary wheels, Peter Lux. So in 1962, Zaharov and Sharp proposed the metric form last pair for the nonlinear Schrodinger equation and used inverse scaling method to study the inverse scaling transformation and the exact solution of the nonlinear Schrodinger equation. In 1964, Ablois, Cope, Norway, and Sugar proposed a class of the integrable system with the unified Lux pair form, known as AKNS system, and established the universal framework for the inverse scaling series for the initial value problem of the AKNS system. Then, many classical integrable systems with last pair were proved to be the solvable with inverse scaling method, which was also considered the milestone in nonlinear science. Therefore, last pair provided the theoretical base of the construction, the general frameworks of the inverse scaling series for integrable system, promoting the development of the integrable system series. Example, the KdV equation. This one possesses a last pair. This, the compatibility condition for about last pair 2 and 3 is equivalent to the KdV equation. In general, a nonlinear PDE is said to be less integrable if it can be written as the compatibility condition for such a system of the linear equation. Last integrable ability. If the nonlinear partial differential equation 4 can be expressed as a compatibility condition phi xt and phi tx for the pair of the linear equation is 5, where the compatibility condition is equivalent to 6. Then the equation 4 is said to be the last integrable. The pair of the linear equation is called the last pair for equation, and the equation 6 is referred to be as the zero curvature equation, zero curvature equation. Two forms of last pairs. Operator form, the KdV equation with last pair. Operator form as follows. You can see matrix form, the nonlinear Schrodinger equation with the last pair can be written as. So this is matrix forms, this is operator forms. So last pair and inverse scaling transformation from U0 X by space part of the last pair scaling process, you can get scaling data, time evolution. Yeah, solve the GLM equation inverse scaling process. Okay, step 1, map the nonlinear integrable system to relevant linear directly scaling problem. That is, from the initial potential to the scaling data S0. Step 2, calculus the time in evolution of the relative linear scaling data. Step 3, solving the inward scaling problem and determine the integrable system dynamical of time in value based on the involving scaling data. Last pair, informed neural networks. Node, LP, last pair neural network target tellers for the integrable system with last pair comprising last pair neural network V1 and last pair neural network V2. The advantage of the last pair neural networks for some integrable system with simple last pair. Focus on the simple last pair. Last pair neural network V1 can solve this integrable system with last pair to obtain the data-driven localized wheel solution, spatial parameter, and spatial function, and possess the fast training speed.
Can I ask what is a simple last pair versus a
Last pair
non-simple?
means you can say, for example, I give the 4 example with the last pair is you can from the formals. I give an example to explain this.
Okay.
For another integrable system, beside the four mutation once, last pair neural network V2 can solve data driving localized wheel solution and associated to a spatial problem and achieve high training accuracy. Yeah, the application of the last pair neural networks. Last pair neural network V1 obtained the solid solution of the KDV and now smooth peaking solution of the Kama's-Holm equation. Line solid solution of the KP equation and the lamp solution of the high definition KDV equation. You can see this the 4 equations with last pair relatively simple to relatively simple, but LP last pair neural network V2 obtained the kink solution of the Sein-Gala equation. You can Sein-Gala equation is complex. Solid solution of the modified KDV equation and the Roger wheel solution of the Nonlinear Schrodinger equation and the pulse and the solution of the short pulse equation. last pair informed neural networks. Neural network part with unknown parameters. This is a neural network. The last pair informed part with the spatial parameter lambda, auto differential, automata differential, last pair and related constraint. You can see the last pair neural network V1 only used the last pair of the integrable system. And on the basis last pair neural network V1 and can go to the V2 last pair neural network plus this operate form compatibility condition equation, matrix 0 curvature equation. So this is lost reduce lost function, lost equation. So the first is just like to the PINN, initial of the bounding problem. Is initial bounding from data loss. But this is replaced physical information. The collocation of the points is a residual loss of the last pair. So you can see one is L last pair neural network. This is second is V2, the plus residual of the loss compatibility condition, or zero curvature equation. This pass just to the physical information. Okay, the total loss. The total loss function are, last pair neural network 1. This is initial abounding data loss, this, and residuals of the loss last pair, and residual loss compatibility condition equation for the last pair operators form this. Okay, residual loss of zero curvature equation for last pair of the matrix form. Okay, so V2 versus the V1. This is some of the number of the elements in initial and the bounding point set. The number of the elements in collocation points set, and L normal, and learning result of Q action 1 and measurement data, and F is value of complex condition equation, and value of zero curvature equation. So application for the PINN and last pair pins. PINN is plus the physical information, nonlinear partial difference. Last pair neural network V1 is last pair information. Integrable system with the last pair. So this is a special nonlinear system. And the last pair V2 physical information plus last pair information. Yes, integrable system with the last pair. Our deep learning method involved the PINN and last pair neural network. Both possess 5 hidden level and with 100 neuron on per heading level. The named L equal to 6 and ND equal to 100. Application of the last pair neural network 1 in the KDV equation. The KDV equation is a PDE that describes the motion of the water wheel. It is one of the most classical equations in the solitary series and the integrable system. We consider the KDV equation with the last pair operator form and consider initial condition and the bounding condition as follow. This KDV equation and initial bounding condition. This you can see the training time. This is okay. So application of the KDV equation is solitary solution and spectral for function phi. So we consider the classical Kamath-Helm equation. It's arise as a model described unidirection propagation of a shallow water wheel of the flat bottom, where U xt precipitation of the height of the free surface about a flat bottom of the river contains omega being the relative to the critical shallow water speed. The Kamath-Helm with omega equal to 0 possesses of the following last pair. You can the equation is complex, but the last pair is relatively simple. We count the initial condition and the boundary condition as flow. You can pick in a solution U and spectrum function phi. In contrast with the numerical result of KDV equation, the training of the Kamath-Helm equation in this is signature more efficient. It's benefit from the complex of the last pair of the Kamath-Helm equation and KDV equation. It's not signature different, but the form of the Kamath-Helm itself is more complex than that of the KDV equation. The pink solution in this case is now small solution, indicated that the last pair neural network V1 is also cumulative of the implicitly solving non-small equation. You can say this is the result of the training time. Just the normal error is nearly. So I give to lambda. The further invite performances of the LP NNV1 in high definition integrable system, we consider the type 2+1 definition integrable PDE in this example, named the KP equation. KP equation can be written as KP2, KP1, KP2. The KP equation is natural generation of the KDV equation. The last pair of the KP equation can be written as. We consider initial condition and the bounding condition of KP2 equation as follow. So you can see line solution, solution, spectral function. Okay. So compare with PINN, LPNV1 is not only reduce training time, but improve the training accuracy by about 2 times. Numerical result indicated that LPNV1 is said to suitable efficiently solving the high dimension integrable system and their last pair spatial time. You can see this result. Last pair 1 significantly improved the training efficient in the solving non-small solution and study the high dimension integrable system. With the training accuracy is similar to the even higher than the standing PINN. Usually, high definition integrable system their self have the relative complex form, where their last pair have a simple from forms and compare with the PDE itself. Hence, LPPNV1 is particularly suitable for the study high dimension integrable system. So, in this part, you further consider the following high dimension KDV. With aid of the bare polynomial series, we derived the following last pair. We can derive the high dimension KDV equation with a compatibility condition as equation. We consider infinite initial condition and the boundary condition as follow. We can get these results, a lamp solution and the spatial function of phi and the training time of this. Okay. Application last pair neural net V2 in the Sine-Galois equation. Sine-Galois equation and the last pair can be replaced as you can see this last pair is a complex compared with the Sine-Galois equation. So we consider initial and bounding equation condition of the Sine-Galois as follow. So you can kink solution U, spatial function and spatial function 2. So PINN have the shorter time training time. Last LPNVR NV2 have the highest training accuracy, where LPNV2 have both training time and training accuracy at the intermediate level. Because of Sine-Galois information, Sine-Galois form is more constant compared to its last pair. So LPPV1 cannot complete efficient training, but LPPV2 can achieve higher training accuracy. You can see this. But because the two constants, because you can see training time is this. So the KDV equation, which was derived of study of the unharmonic lattice, yet also the most important models in the integrable system, and can be regarded to as a KDV equation with carbon nonlinear. And exact solution of the KDV equation and modified KDV equation can be transformed into another with the Muller transformation. The modified KDV and its last pair, initial and bounding condition, you can see the last pair is complex compared with the equation. So you can, I use the LPP, we use the LPPNY, got the results, but the time is long, but the accuracy is okay. It's better. So integrable nonlinear solution equation is close to relative to many nonlinear problems in the field, such as nonlinear optic plasma and Bernst context, the potential function of the nonlinear system is complex. The value function is also the most class integrable system integrable model in integrable system plays the crucial roles in the integrable system cells. The nonlinear equation with the last pair and the initial bounding the value of the condition can be written as you can see the last pair is complex with the equation. So this results you can see that the accuracy is very good, but time is long. So the short path equation and is last pair. Yeah, this is with the last pair. This we consider in initial bounding the value condition as shown in the follow. So the pulses U and spatial function and spatial function 2. So you can see these results. Summary. By means of the replaced and assisting the PDE in PINN, we introduce the most important feature of the integrable system, named the last pair, into deep learning neural network to propose the neural last pair neural networks, including last pair neural network V1 and last pair neural network V2. The most noteworthy advantage of last pair neural network V1 is that it can be transformed solving the nonlinear integrable system into the solving the linear last pair spatial problem. It's not only efficient solve data-driven localized real solution, but also obtain the spatial parameter and corresponding spatial function of last pair of the integrable system. The major advantage last pair neural network V2 is ability to solve obtain the high accuracy data-driving localized real solution and associated spatial problem for integrable system with last pair. Last pair neural network study KDV equation, Kamos-Cobb equation, KP equation, and the high definition KDV equation, obtain the data-driving Soliton solution, North-Marshall peak solution, line solution, Soliton solution, lamp solution, spatial parameter, and corresponding the spatial function. Here, training time of last pair neural network V1 is was more than 2 to 5 times faster than that one of the standing PINN. Last pair neural network V2 study Chen-Yong equation, modify the KDV equation and nonlinear equation and short pole equation with high accuracy and obtain the kink solution, Soliton solution, Rogue-Wheel solution, and pause solution. KDV, integrable 5 famous equation. KDV, Schrödinger equation, and nonlinear Schrödinger equation and Chen-Yong equation. It's 4 famous, and I'm KDV. So the research work of this article further promoted the development of the framework of the integrable deep learning method and provide a new idea and approach for the numerous spatial problem of the integrable system. The discovery of new localized well solution and even new last pair. Thanks. Yes, photo with my students. This article is Pujing Cai. Yeah. Thanks.
Oh, okay. Thank you, Dr. Cheng. It was a really nice presentation. You got really nice results. Do you have any questions from the audience?
If we, in all of these cases, you did know the lax pairs in advance, yes?
What?
You already knew what the lax pairs were, yes?
He derived them, Yanis.
Yeah.
He derived them.
I don't know.
This happened before the numerical solution, during the numerical solution?
Numerical solution, yes.
I
don't know.
Sorry if it's not
if
clear.
I don't know the last pair, I cannot use this method. Yeah, I must know the last pair.
So if somebody told you that the lax pair exists, but you do not know it.
Yes. But another the features of work I can see from the equation, and if you know some of the three Soliton solution, we can, I think I can found the target is found the newer last pair, because this works we can find the partial phi and partial lambda, spatial phi and spatial lambda. I think the inverse problem.
Okay, thank you.
Because it's open problem in the found the new last pair, so a long time. So it's open problem. I think next work I will be study this from to equation. From equation have, if we have the three solid solution, we can find last pair. I think very interesting.
Dr. Chen, I have a question about the lax pair version 1, V1, that so V1, the accuracy was not very good, not very high. Of course, I know it was a little cheaper than PINN, but when do you use V1, especially in the last example? I thought in the very last example you showed, I thought the V1 didn't converge. So what?
I know your means, but I think yes, compare with PINN, yes, so because study is very famous equation with relative simple last pair. So I numerical experiments will give us some answer. Okay.
Also, I have a question on
because linear, you can say the famous equation with some last pair. First is linear. Second is direct order is low. So if some of the acute situation need to speed, I can say use the LPNN1.
Okay. Can I ask another question on the Mura method that you showed, which you connect the modified KdV with KdV. So the Mura transformation, the solution of the KdV is I guess the square of the Mura of the modified plus the derivative, right? So how do you are you computing in the loss function you have the modified KdV, and then after, because it's easier to compute, right? That's why, because the V squared term becomes
and Mura yes article you can see this. Because if you know this the Mura transformation is two scheme, the scheme 1 and scheme 2. This is a KdV equation, initial bounding data theta. From this, you can go to this modified KdV equation. Mura transformation is this KdV initial bounding data theta from the initial bound data. So from the KdV and training and scheme 1 and scheme 2. Scheme 1 is F1 is KdV, F2 is Mura transformation, F3 is modified KdV, MKdV. So you can this the scheme 1. Another scheme 2 is this is like the PINN. As PINN, just use the initial and bounding data. You can go to this U, it's KdV solution. Then a second step 1, step 2, just plus the Mura transformation and modified KdV equation. So you can go to the is the solution of the modified KdV. So you can find a new localized VL solution before I can see this. Okay. As not report this new the Kink-Bell solution. Okay.
Great, thank you so much for explaining that part. Do we have any other questions from the audience? It looks like we do not, but maybe I have a question. In all your models, you were using like LBFGS. Is there a reason why you didn't use Atom? Because that's kind of like what normally we use.
Yeah. Our workers mainly use the second order LBGS optimeter for the optimization, as the LBFGS optimeter performs better of the numerical experiments.
Oh, okay.
Yeah, despite being the more expensive to us to use. In fact, we can use the ADAM, our SGD for optimated. We have a conduct numerical experiment on some example. Numerical results show, I do a lot of the numerical experiments. The results show the LPNNS can still outperform after use ADAM optimeter.
I see, I
Yes.
see. That's nice. Thank you for
Mm.
explaining that. And also, how when you were like computing, was the total time? So you ran all your models for the same number of iterations, right? That if I understand correctly, because you
Sorry,
keep it like,
you
for
can
example,
be repeat that?
yeah, sure. When you did your benchmarks, all your models, you ran them for the same number of iterations, right? Because, for example, in the first example that you showed, if I remember correctly, the your your model, like the version 1, it took like 63 seconds, and the PINN took like 300 seconds. But the error was like the third part of it. So what I'm saying is like, how did you know when to stop? Did you stop training based on the number of iterations, or when the model reached some type of convergence?
Okay, enough. So just the I think I know your means the KDV equation. Yeah.
Yes.
How to say? Just I think is stop. Just have the how to say data. Sorry. Iteration.
Is iteration based?
Iteration. Yeah.
Okay, great.
Okay.
Thank you. Do we have any other questions from the audience? It looks like we do not. Okay. Once again, thank you so much for your time today, and we're really sorry for the small inconvenience we had. It was really nice to have you. And with this, we only had one speaker for today, so with this, we may close the session for this week. Thank you so much, Professor Chen. And this was a wonderful talk. Thank you so much for sharing your insight
Thank
with
you,
us.
Kendall. Johan Kendall. Your name. Yes.
Oh, my name? Oh, my name is Juan.
Juan.
Juan. Yeah. Yeah.
Juan, like the Chinese Huang. Yeah.
Yeah.
Okay.
Yeah. Okay.
Welcome.
Thank you so much. Okay. Have a wonderful day, everybody.
Thank you. Okay.
Thank you.
Okay.
Bye.
Bye.
Until next week.